Hello, my name is Erica. Some of you might know if you've already seen my other video, but today we are going to talk about the fundamental theorem of calculus. And so, first we're going to start off with the theorem, and then we're going to summarize and work through it and point out what's important in this theorem and what it means and what its purpose is. And so, this time I wrote it all out, so that way I'm not writing the middle of things. Might make it a little easier, we'll see. But the theorem states that let f of x be a continuous function defined on the interval, then f of x, capital F of x, equals the integral of f of t on the interval of x to a, and this is an antiderivative of lowercase f of x. And so then, if capital F of x is an antiderivative of lowercase f of x, then this is what should be equal to each other. And so, why are we doing this? What do we want to find? Okay, so the purpose of this is that we want to demonstrate that this, what f of x, the capital F of x, is equal to, is the antiderivative of f of x. And so, in other words, we are going to have the derivative of this capital F of x equal to f of x right here, the lowercase f of x. I apologize if that's a little confusing. So then, the way that we're going to do this is we are going to plug in the definition of a derivative. So if you remember from the definition, it is you have f of x plus h minus f of x. And so here we are going to plug that in to the equation that we have here. And so what we do is we get the derivative of f of x is the limit of, as h approaches 0, 1 over h, which is the same as putting this over h. And we plug in x plus h here and x there. But we don't want the a to x part. So if you look down here, we have a graph, and we have a, x, and then x plus h, but we don't want that part. And so what we do is we just reverse that. We reverse that sign right there, which means that we also flip this, and the a's cancel out, so we get the x on the bottom and the x plus h on the top. And so, given this, here's some sticky notes that I just wrote for myself that you don't need to see because they're not that pretty. But, okay. So, now we have to continue showing why exactly and how exactly these equal each other. And so right here is a modified graph. And so as you can see, we have our x and our x plus h, but we want to show that it's continuous, okay? And so we have 2 endpoints because we want to show that this equation is continuous on this function. And so what we have our points there, right? And then we are going to establish a minimum on that interval and then the maximum on that interval. And we do this by essentially finding the area, because if we multiply, because this is h, because if you since you're adding h to x, then that would mean that this region right here is x, or h. And so to find the area of this little rectangle and then this tall rectangle, we will multiply little m, which is the minimum, times h, and we would also have the uppercase M times h, which will get you the area of this big rectangle and then this little rectangle. But what we're trying to say is that it's within this area, and so we find that technically by subtracting this little area from the overall area, because the M represents the overall area. The uppercase M represents that big rectangle encompassing the little rectangle. And so, how do we do this? Well, assuming that h is greater than 0, we are just going to divide right here. So we divide to get the minimum instead of the area, and so we just get the this distance right here. And so we divide by h for each of these, okay? And the reason we're assuming that h is greater than 0 is just to not complicate this, because if it was less than 0, well, then we'd have to flip the signs, and we're just going to go with this for now. And so this should look familiar because we were looking on this on the previous page. And so the way to further prove this, to prove this whole point right here, is that when it's tested that as h approaches 0 from the left and the right, that they're both going to equal f of x. So this is showing that yes, indeed, f prime of x equals f of x and is continuous. And so here we have our, we have showing that we're plugging this in here. So this is what f prime of x equals to f of x, because that is what we just showed. But, so now to explain a little bit more, so we know this is continuous and we know this is differentiable, but how does the mean value theorem actually apply to this, okay? So we were trying to find the slope between the 2 points, but we're also finding the tangent line on this graph to the line that's connecting these 2 points, okay? And so this is the fundamental theorem of calculus is essentially finding this slope right here, okay, between the 2 points. And what we do by the mean value theorem is, which is this equation down here, if f is continuous on the closed interval a of b and differentiable on the open interval a, b, then there's a number c in that open interval such that f prime of c equals f of b minus f of a over b minus a, which is just saying the change in y over the change in x. And so the mean value theorem is applied to show this tangent line right here. That's tangent to the one between the 2 points. And this right here technically is very similar to this. And so by applying the concepts of the mean value theorem and finding a slope and applying that to the fundamental theorem of calculus, we are shown a graph that can in fact have the fundamental theorem of calculus applied to it as continuous, and we're able to show that, okay, these two functions do equal each other, and also get the tangent line to those 2 points. And that is a lesson for today. Thank you.